It's nice to give my first talk here. Okay, so I'm going to talk about cliques in hypergraphs. But I'll start with some motivating or background material. So let's say background. So in extremal graph theory, one of the classical topics of extremal graph theory, it's the two-run type extremal problems. And basically we're interested in the following. I'll tell you what that means. It means the maximum number of edges possible in a graph which has n vertices, but there is no h subgraph. Okay? So h is a forbidden subgraph. You have n vertices, and it's basically asking how many edges can you put into your graph on n vertices, but avoiding that you make this as a subgraph. Right? And that's one of the classical topics of extremal graph theory. When h equals the complete graph on r vertices, this is Turon's theorem. I'm not going to say how many there are, but Turon's theorem characterizes exactly what the graphs with the maximum number of edges are. And then the classical starting point of extremal graph theory is the following, which says that this number equals, let's see, times n choose 2 plus a little o of n squared. So this is the Adderstone Theorem, or it may be Adderstone-Simonovitz. Is it right? Okay, so it says that if the chromatic number, you know the chromatic number of the forbidden graph H, then you can have at most this many edges, right? And this is considered the fundamental theorem of extremal graph theory. That's what they call it. Right? Right, only the chromatic number. So this is a very nice result. Right? There is one weakness with this result, and that's for the case when H is bipartite, two colorable. This term vanishes, and it just says that you have little o of n squared edges. Right? So then that's the only case when this theorem doesn't describe very much. But there is a case when you have KAIST. This is the complete bipartite graph. S vertices on one class and T vertices in the other one. And in this case, it is known that this is some constant times n to the 2 minus 1 over s, I think it is. Let me keep my... And this is the Kováry-Turon theorem. So that takes care of, in a sense, the situation when it's a bipartite graph, except that only when... So this is known to be tight. This is tight for S at most 3, or what is it? S minus 1 factorial. So when they're very unbalanced, okay, then it's known that that is actually the tight bound. Okay. And all of these come from some constructions from finite geometry. So these lower bound, to show the matching lower bound. Okay. Everything clear so far? Yeah. And to close this lower bound, I think that's one of the major problems in this whole theory. Okay, so that's sort of the background. Let me tell you what I'll go over here. recent trend, some recent trends. So two recent trends. Alon and Schickelmann consider the following variation: EX N T H. And what does it say? It says it's counting the maximum number of subgraphs of type T. So you fix a graph T, you fix a graph H. You have a graph on, now you look at a graph on n vertices, right? You count how many copies of T can you have without getting this H as a subgraph. Okay? So in this notation, the previous EX and H is EX and K2, which is an edge, H, like this, right? And they, for example, one thing that they prove in their paper, so this is from maybe 2015 or something like this, they prove EX and KM KST is at most C M S T n to the m minus m choose 2 over s. Something like this. And again, tight in the same region as this. T's, which T? This T? Oh, yeah. You're simply counting, you're looking at a, so say T has 5 vertices. Yeah? You're just looking at those 5 vertices, is T there? Yeah. Like here it's very simple. You just look at the m tuples of vertices. Is it complete or not? Yeah, good question. So I don't really know how much they studied when this varies. Yeah, but they introduce it in this general setting. And like I said, again, this is typed in the same region. And another recent trend, this is by Low, Tate, Timmons, one more, Zhu. They consider the following: EX N, comma, H, F. Okay, so this is again an extremal parameter. You have a graph on n vertices, and this is now the forbidden things. H is a forbidden subgraph. F is a forbidden induced subgraph. Okay? And then how many edges are you able to put in on n vertices? What is the maximum number of edges you can put in n vertices so that you don't get H as a subgraph and you don't get F as an induced subgraph? I'm not going to say what induced. You know what induced subgraph means, right? Yeah. And you can't just forbid, if you forgot this H, you might think, well, let me try to define the parameter EX and F induced, right? If that F is not a complete graph, then this makes no sense. You just put in all possible edges. You will never induce that graph F, right? So that's why you have this extra guy here, right? And so one thing they prove, maybe their main theorem, but they have a bunch. They start a systematic study of this. They call this forbidden induced two-run problems. And one of their main results, KR, KST induced. This is at most some constant C or ST, n to the 2 minus 1 over s. The same bound, except the constant maybe changes a little bit. Yeah. Yeah, but proving it is somewhat different than that, right? Because now you're looking at this induced thing, and that kind of changes the game a bit. But the interesting thing is that you essentially are getting the same value. Yeah. Where do these notions come up? Okay, why do we want to study these? Is that the question? That's a good question. I don't really know. I mean, it started here. I don't know why he studied this, actually. Just a natural question to ask when you're looking at substructures in your graph. Yeah? And then you might ask, yeah, so I think the natural thing is just how dense can your graph become before some kind of structure happens there, right? But I will maybe give I will give a relation to other things later on. Yeah. Okay, so this is actually my starting point, not exactly this result here. Already when the case S equals T equals 2, this is somewhat interesting. Yeah, this result here. And it was studied in a different form by Gyárfás, Hubenko, and Solymosi a decade earlier than these guys, roughly. And they showed the following. So suppose G has n vertices and alpha and choose 2 edges. Okay, so we have a dense graph, right? And then if G has no induced K22, then the clique number of G is at least C squared over 10 times n. Okay? So it's related to this theorem here with S equals T equals 2, right? So we know that if you fix K, if you forbid this KR induced subgraph with any R fixed, right, you get a subquadratic number of vertices. Sorry, a subquadratic number of edges, right? So the way that they looked at this question was, forget about the forbidding that complete thing. Just look at how we know that if you put in a dense graph, so really quadratic number of edges, then, sorry, they shouldn't be alpha, they should be C. You put in this quadratic number of edges, KR is going to appear for any value R, right? And this is measuring how big that complete graph is getting. Right? That's what it's measuring here. So it's a similar problem, right? Just from a different viewpoint. And this is the theorem that I want to somehow generalize. Okay, so yeah, so all these things so far are about graphs. Now I want to think about K-uniform hypergraphs. Okay, so that's 3 K-uniform. So that is, a graph is a 2-uniform hypergraph, right? It's a set of vertices and a subset of the pairs. Now we look at a set of vertices and the subset of the K tuples, right? K element subsets. Those are now called the edges. So then we could ask, how does this generalize? in a K uniform hypergraph? Any suggestion? Yeah, okay. Yeah, maybe. Okay, I'll give you what I found was a reasonable generalization. So, okay, the key thing was that when you go to K uniform hypergraphs and K is greater than 2, it's too strong to look at induced things. You need to look at some kind of not quite induced. That's why I call it forbidden substructures. Okay, so let's start with H. This is a K uniform hypergraph. So it's a set of vertices, set of edges. The edges is a subset of the K element subset of V. Yeah. And for convenience, I'll define M. This is these are the missing edges. Okay. So those are the K element subsets that are not there. And so what I want to define is an analog of that, which is, I'll call it a complete M tuple of missing edges. It is, so it's a bunch of missing edges like this. There are M of them. These are missing edges. And whenever you choose one vertex from each of them, so take K vertices, 1, 2, 3, from any there, that is an edge. Okay? So equivalently, if this is tau 1, tau 2, tau n, these are pairwise disjoint missing edges. And then for every ti in tau I then is set T1 to Tm is a clique. So it's a complete sub-hypergraph. No, I'm defining what a complete M tuple of missing edges is. So you take K guys, not an edge. Another K guys, disjoint, not an edge. Another K guys, not an edge. You take M of those. And all of these, any choice of K from distinct should be an edge. That I will call a complete M tuple of missing edges. Okay. Of course, M is at least K. This is not as for K. Okay, so let's look at a special case. K equals 2. If M equals 2, right, it means here's a pair, it's not a missing edge. Here's a pair that is a missing edge. Here's a pair that is a missing edge. But this edge is here, this edge is here, this edge. That's precisely an induced K tuple. Right? If you have M is larger, it means here's a missing edge, here's a missing edge, here's a missing edge. And it's complete. And it's really an induced subgraph, right? On those vertices. But when I have when I have K is greater than 2, this is not an induced subgraph because I don't know anything. I don't know if these two vertices and these a few more vertices here, I don't know if this edge is here or not, right? I have no information about that. Right? The concept of a complete M tuple of missing edges doesn't say anything about that. It just says that you have M disjoint missing edges, and all the transversals should form edges. Any transversal or any partial transversal should form an edge. Okay. So that is a complete M tuple. Is it clear? Yeah. And so I'll delete these examples. So when K is 2, this really is an induced subgraph. Well, it's a K-uniform hypergraph. So you could either...
I see.
Yeah.
So any something.
Yeah, exactly. So another way to say it is, whenever you choose K vertices from distinct missing edges, that should form an edge. Right? Or you can say that any full transversal forms a clique. Yeah. And so here is what I proved. Not super complicated, but I think the reason was that nobody thought about what should be the generalization of an induced K-tooth. So the theorem, maybe you can, now I will not use C anymore, I will use alpha. So for every M, and alpha in 0, 1, there exists a beta. It should depend on these things. Alpha Km is positive, such that so H, this is a hypergraph, n vertices, and CMH, I'll say what that means afterwards. If H has no complete M-tuple missing edges, then the clique number of H is at least beta times M. Okay. Cm, this is the number of cliques on M vertices. Okay. So here, it's sort of an analog of here. I'm not necessarily counting the number of edges. I'm counting the number of some kind of induced subgraph, in this case cliques. And yeah, then this is the clique number. There's going to be a clique that is of a significant portion of all vertices. Right? And so it seems that this is the correct generalization of this forbidden induced substructure. Right? I mean, and already for k equals 2, but arbitrary m, this is a kind of generalization of the one here, right? And you see that you cannot generalize. So let's say m is 3 and k is 2. Basically, it says that m is 3, k is 2. It means that this guy that I drew before is forbidden. This is forbidden induced subgraph, right? And it illustrates why you need to deal with this parameter, not the number of edges. Can you see a counterexample? So if I forbid this as an induced subgraph, can you give a counterexample if all I require is that I have a dense amount of edges? So I have alpha n choose 2 edges, but this one is forbidden induced. Is there a counterexample to this one? Yeah, say complete bipartite graph, right? Complete. Yeah. It's dense. It has none of these. Clique number is super low. Right? So you really need to go up to, really need to look at this. This is the right thing to look at. Yeah. And it works in every dimension. So I think of the uniformity as the dimension sometimes. And this is this property, the property that that this hypergraph has when you forbid this. I'll give it a name now. I don't know if that's the final name. So this is some concentration. Let's call it the strong concentration property. Basically, the reason that we're interested in this property is it's saying something that if you start putting in a positive proportion of all possible edges, they will, by forbidding this guy, those edges will lump together and concentrate into a clique, right? When you don't forbid something, that is not happening, right? That's precisely, and you can make these complete bipartite graph or complete multipartite graphs. You put in really a dense number of edges. The clique number doesn't have to be very big. But by forbidding something, then you get this concentration property. That is something that, for reasons that I will get a little bit into, we are HSK uniform. We are interested in this. We are interested in understanding what kind of graphs and hypergraphs have this strong concentration property. That is a very beneficial property. And this is a new theorem that says, here is a condition that gives you strong concentration. Right? And I want to give you some more examples of the strong concentration property that have been studied. So I kind of had a diagram I wanted to draw up here. So it'll be too much to say to point out all the reasons why we are interested in this strong concentration property. I can instead just show you where it has been studied earlier. Okay? So the initial theorem I deleted here by Solymosi was forbidden induced K22, right? So no induced K22. Now, one so subset of graphs with no induced K22 are things called Chordal Graphs. The subset of them. Right? These are graphs whose smallest cycle, induced cycle has length 3. Right? It's known that these are precisely the so here I'm going to look at intersection graphs and of subtrees of a tree. Okay, so those are the chordal graphs. You fix some tree, or take any chordal graph, and you look at there is some tree, and you can make that chordal graph as the intersection graph of some subtrees of that tree. Yeah, those are the same. A subset here are the intervals on a line or paths, or okay. These are all examples of graphs that have no induced K22. Right? And it's been known for a long time that these guys have a concentration property. Okay, so these guys have this strong concentration property with this beta equals 1 minus square root of 1 minus alpha. That's a known theorem. And well, that's been known for a long time. If we go down to here, the sort of least general case, there is another way to generalize this. So intervals on the real line, that's just an example of convex sets. Okay, so you could generalize this into convex sets in RD. Okay, and you can look, instead of their intersection graph, you now look at the intersection hypergraph. And due to something called Helis Theorem, you're actually interested in the d+1 uniform intersection hypergraph. Right? You're interested in which d+1 of them intersect. You have a bunch of convex sets in RD. If you record which d+1 are intersecting, you kind of know what all the large intersecting subfamilies are. Because the cliques in this intersection hypergraph are precisely the intersecting subfamilies. So you can look at this one. If you want, you can go to the clique, what they call the clique complex. So that's just the simplicial complex on the same vertex set where the faces are the cliques of that graph. Right? And you could also go here to the Chordal Graphs. The Chordal Graphs, go to the Clique Complex. Then you arrive at something called one-Leray complexes. I won't say what that means necessarily, but it generalizes, just like this generalizes convex sets, to something called d-Leray complexes. And what does it mean? It means that the K is d-Leray complex. If every induced, so this is an induced subcomplex, has vanishing homology in all dimensions d and above. Okay? And so this is sort of the picture of all these structures that we are interested in. And yeah, you generalize intervals to convex sets, you look at the intersection hypergraph. Turns out when you take the Clique complex of this intersection hypergraph, you get a d-Leray complex. Okay? And it's not hard to show that Chordal graphs, if you look at their Clique complex, there is no one-dimensional homology or above. If you look at any induced subcomplex. Okay? That's maybe easier to see, right? If this was an induced cycle, well, that's one-dimensional homology, right? But since this is a chordal graph, it means there's a chord here and there's a chord here. It kills those cycles. These are not one-dimensional cycles in the Clique complex because now you fill those in, right? Because these are cliques. These are triangles. You fill them in. You kill the one-dimensional homology. And that's kind of the same thing that's happening. Okay. And let me state the theorem here. This is a very well-known theorem for people in my area due to Kalai, which says that these d-Leray complexes have the strong concentration property with beta equals 1 minus alpha, the 1 over d plus 1. And the one-Leray case is precisely the Chordal graphs. And then, I don't want to get too much into it, but they have then derived that this strong concentration property implies a lot of other things. Things that independent conjectures were made about intersection structures and stuff like this. And it's sort of, after a lot of work, a big theory been developed, and they've realized that it's this strong concentration property that allows you to prove a lot of stuff. So that's something very nice, something that we want. Right? And the proof of Kalai's theorem. The only known proofs of Kalai's theorem is, let me put this in parentheses, by the way. Just the fact that you have the strong concentration property, this is some algebraic proofs. He uses some technique he invented called algebraic shifting in the exterior algebra. It's quite technical. And there are now other proofs, which is something called symmetric shifting, which is some commutative algebra approach, and everything gets into somehow commutative algebra. That's how you prove this, right? And Kalai is one of the people who has asked for a long time, give an elementary proof that D-Leray complexes have the strong concentration property. And the reason is that since the theory has developed, we know now that the strong concentration property is going to imply a bunch of stuff. It's something we really want. Those algebraic proofs of this using the commutative algebra, they're very specific to this condition. Right? The D-Leray condition, if you go to something called the Alexander dual, you get a complex which is what they call Cohen-Macaulay, which Stanley and company have sort of mined out completely. They know so much about it, right? But as soon as you start looking at somewhat uglier complexes than D-Leray complexes or Cohen-Macaulay complexes, these tools don't work very much anymore. So that's why it's nice to have some elementary proof. It would be nice to have an elementary proof that you have the strong concentration property for these, because then you could maybe extend it to other things. And this theorem is one such example, right? And actually this theorem will imply this, that you have the strong concentration property, not with that constant, which is not to be expected because forbidding this complete M-tuple of missing edges is a much weaker property than the D-Leray property. D-Leray property is deceptively complex, or in a sense, it's a very global property. It's a property that you need to check over every induced subcomplex, right? It's a property you need to check the homology of every induced subcomplex. This is a much simpler property. You check every subcomplex on M times K vertices, or a subgraph, right? It's a local property. That is a global property. Yeah. So it's much simpler property. But still, you get the concentration. So let me show why this one implies, why that one implies strong concentration property here. This is the part I'm most worried about because you're going to think I'm cheating. Okay, so 5, proof of Helis theorem without the numerical bound on the beta, just proving the strong concentration property. So you need two facts. Fact 1. If K is D-Leray and complete D skeleton, then K is a simplex. Okay? So if you have a D-Leray complex and the D skeleton, every possible base of dimension D is there, well then it must just be the entire simplex. Okay? Just imagine for D plus 1 vertices, or D plus 2 vertices. So if every, let me do it simpler. D is 1, okay? D is 1, and let's look at these 3. Okay, this edge is here, this edge is here, this edge is here. If that is not a face, you made one-dimensional homology, right? So then you do that, it means that all the triangles are there. Now let's see another one. All the triangles were there. Well, if that is not a simplex, there's two-dimensional homology there, etc., etc., etc. So it just builds up and you fill in the hole. That's not cheating. That's very simple. Here's fact 2. Fact 2. That's actually a theorem by Kalai and Mechelen. K is D-Leray. M is a matroid complex both on vertex set V, and M is a subcomplex of K. Then there exists a phase, tau, in K, such that the rank in the matroid of V minus tau is at most D. This is less obvious. It's not obvious at all, actually. It requires some proof. But the proof is some kind of magic trick, which is much simpler than the Kalai's theorem about the strong concentration property of deal array complexes. It's just some kind of magic trick that works. Okay? That's all I can say. So this is the part that maybe I'm cheating. I will need to use this. Right? But let me tell you a special case of this one. Okay? A special case is the following complex, matroid complex, MD plus 1. So you take D plus 1. So there are D plus 1 vertices here. You take D plus 1. So D plus 1 squared vertices. All right? And then you look at the following matroid, which is the independent sets are anything chosen transversely. That's called the partition matrix. Right? That is a matroid of size of rank D plus 1. So this is my M. Now suppose you have a deal array complex K on the same vertex set, which contains M. So suppose you have K, and inside is contained this MD plus 1. What does this say? It says that, well, there exists some phase in K, such that the rank, when you remove that phase, the rank is at most D. Okay? But what are the rank of this matroid is D plus 1. So if you have a phase, and when you look at the complement, you look at the rank of the complement, the rank is at most D. It means that that phase tau must contain it must contain at least one of these guys. Right? Completely. Is it clear? Suppose you take a phase tau that does not contain some vertex here, does not contain some vertex here, does not contain some vertex here. What is the rank of what's left? Well, D plus 1. So in any deal array complex that contains this complex, as a phase is one of these classes here, one of the parts of the partition. Okay? And that, you see, relates to the missing M tuple. Right? So it basically means that if you have a deal array complex, then there is no missing D plus 1 tuple in that intersection hypergraph. And then you just apply this theorem, and you get the strong concentration property. Well, you get a clique. Right? You take the D plus 1 intersection hypergraph. It will have a clique of size at least beta n. But that, yeah, and that beta n, well, that by this first one becomes a simplex. That clique becomes a simplex, so the dimension is large. So that is a proof of Kalai's theorem using this trick by Kalai initially. And then you'll just have to believe me that this fact is a much more elementary fact than this theorem. Right? Which it is. Well, it is because I understand completely the proof of this. I kind of understand the proof of this. No. There's no algebra involved here. Like I said, it's some clever trick using the Alexander dual. It would still be nice with an elementary proof of this, even an elementary proof of just this simple case. I don't really use the fact that it's an arbitrary matrix. Their theorem is for any matrix. Only for this partition matrix. But this theorem tells you that in the D skeleton of a the set of d-dimensional faces in a Deal-array complex, there is no complete d+1 tuple of missing edges. That's what their fact number 2 said. And that's why this one applies there. Okay? 10 minutes left. Maybe not. So I'll just give a quick sketch of what that is. What I don't have time to talk about is that this theorem can be applied to sort of expand this list greatly. We can now find much more structures of intersection, hypergraphs of various things that now have this strong concentration property. So sketch. Proof sketch. And I think I'll just show for k equals 2, and then actually for k equals 2, if you do the calculations precisely, so for k equals 2 equals m equals k equals 2, which is the original Gyárfás Solymosi theorem, then we get this proof that I'm showing you will actually give you beta equals 1 minus alpha squared, which is somehow very strange because it's strange that this 1 minus root of 1 minus alpha appears again. Right? So that's for the no induced K22 case. I think it's a coincidence. I don't know why. But and remember, they had something different. Their original proof was something like beta is at least c squared over 10, alpha squared over 10. That's very bad because when alpha tends to 1, you would expect the clique to become, or when alpha equals 1, you have all the edges, the whole thing is a big clique. You put alpha equals 1 here, it only tells you that 1/10 of the vertices form a clique. At least this one tends to 1 when alpha tends to 1. Okay, so k equals 2, also m equals 2. Let's look at that case. So basically, take a vertex v, right? And then you look at the neighborhood. And up, okay? And inside this neighborhood, I wanted a different color, yeah. Inside this neighborhood, I want to count how many missing edges are here, right? So I'll take a maximal matching of missing edges. Okay, so this is a max matching of missing edges. Has size mu of v. Okay? Whatever number that is. But I do have some control on that number because if I look at what's left, that forms a clique. Right? So this is complete. Okay. And so the number of missing edges. Let's call that m of v. Here's sort of crucial fact. This is at least mu of v, choose 2. So why is that? Well, here's mu of v. That's that complete maximal matching I found. But whenever you look at 2 of them, there's no induced K22. It means that there is some missing edge transversal from here into here. Right? And then you can choose any 2 of these, you see another edge, missing edge, right? Everywhere you look. So the total number of missing edges in this neighborhood is at least that number. And this number, well, using that this is a clique, this number, so mu of v, size of the neighborhood, minus the clique number of that GV divided by 2. That's a lower bound on how big this matching is. Choose 2. right? Okay, so then how large, the size of the neighborhood? Well, that's just the degree of that vertex. Yeah? That's the size of the neighborhood. Now I have a graph that has alpha n choose 2 edges, so it's a dense graph, which means the typical vertex has linear degree, right? So typical degree, this guy is typically some constant times n, right? And so then if you work for some omega, which is less than that constant, this becomes linear. So the typically in a typical vertex, you will see in its neighborhood a quadratic number of missing edges, right? And then you use convexity of the binomial coefficient. You use Jensen inequality, and you get something like the sum of all of z and is something like another constant times n cubed, right? But what does that mean? Well, if you divide by the number of missing edges, which is almost n squared, it means that there is some subset which has linear size, which all see the same missing edge, right? So there's linear size subset S in V, and some missing edge, let's call it E bar, such that E bar is in the neighborhood of every guy in S, right? So that E bar is in NV for every V S. Yeah? So here's where I don't go into detailed calculations, but you can actually get that number if you were to go through the calculation. Well, what does that mean? Well, if there's no induced K22, that linear size subset is a clique, right? You're done. Yeah. And then for K uniform hypergraphs, the proof. So this proof is somehow different than the Solymosi, Gyárfás, Solymosi, and Hubenko proof. Somehow I couldn't see how to generalize their proof. So then how do you generalize this? Well, you need to replace what V is. So maybe I'll try to write up the lemma. That'll be the last thing I do. The general lemma that you have. So in the general case, you have your hypergraph with no, so H, no missing, no complete M tuple, missing edges. You can do the same trick as I did before. You look at, if you look at some subset of vertices, any subset of vertices, take a maximal matching of missing edges there. Then what's left over is a clique, right? And whenever you choose M of these, there is a missing edge that is transversal. And then you double count, and you get that there's going to be many, many missing edges here, right? If you set the clique number small. So that generalizes the first part. That gives you this thing here, right? And then here's the key lemma. So I have this hypergraph, and then let's say that omega h is at most something c half times n. Then for every fi, any subfamily of I tuples with size LEC and choose I, there exists fi minus 1 missing edge tau, such that C prime B I minus 1, so it's large, and sigma union union T is in Fi for all sigma in Fi minus 1 and T tau. So that's sort of the general lemma. That is proved in the same way as here, essentially. Some kind of calculations using Jensen and this observation. So how do you apply this? Well, you start with your whole hypergraph, and now you look at the family of m tuples, which are cliques, right? And by my assumption, that was something dense, C times n choose n, or alpha times n choose n. And then applying that, it says I can find now a family of m minus 1 tuples that is quite dense. And whenever I choose an m minus 1 tuple here and any t in this missing edge, all of those are cliques in my hypergraph. Right? So I got this guy, and I had some subset of m minus 1 tuples. Whenever I take m minus 1 and combine with this, there's an edge there. But then this you apply again, right? With m minus 1. Then you can find a dense set of m minus 2 tuples and a new missing edge. And whenever you take an m minus 2 tuple here, together with some vertex here, together with some vertex here, that is a clique for all possible choices. And you just keep going down. And eventually you'll end up with a linear size subset. M minus 1 missing edges here. If there's a missing edge in this linear size subset, then you have a complete tuple of missing edges, or else that must be a clique. You sort of build that down like that. And that's sort of how you prove it. And some calculations along the way. First version, I actually computed the function that I would get when I get here, but it was so ugly that I deleted it from my manuscript. So I have some theoretical bound. Okay, so I think I'm done.